Good morning. Today we are going to study how Bohr's model successful to explain the stability of atom and hydrogen spectrum. We have studied in Rutherford model that Rutherford model could not explain the stability of atom and hydrogen spectrum. In these 2 points, that Rutherford model was failed. So the next model what we have studied, that Niels Bohr model. In the Niels Bohr model, you have studied the 4 postulates. So we are going to take the second postulate. What is the second postulate in the Bohr's atomic model? The second postulate is given that an electron revolves in an orbit. The energy of the electron does not change. When an electron revolves in an orbit, the energy of the electron does not change. Or you can say, when the electron will revolve in any orbit, the energy of the electron is not going to be changed. But in the Rutherford model we studied that was given by the James Clerk Maxwell, that when electron revolves in the orbit, it is under acceleration radiate energy. But what changes, that Niels Bohr model it is given that electrons revolve in a fixed orbit, fixed radius, fixed energy, fixed velocity, and when the electron revolve in any orbit, the energy of the electron does not change. So when the energy of the electron does not change, there is no question for the collapse of the electron into the nucleus and collapse of the atom. There is no chance that the electron will fall into the nucleus. It means any electron in any particular orbit, can move permanently. There is no hindrance, there is no disturbance, there is no loss of energy. And if there is no loss of energy, then electron can move permanently in a particular orbit, and then the stability of atom will be. So we will see. And the second explanation, that second one is the hydrogen spectrum. In the hydrogen spectrum, you have seen that line spectrum is there. In the hydrogen spectrum, you have seen that line spectrum is there. And these different line spectrum correspond to different frequencies. But in the Rutherford model, it could not give the line spectrum. That Rutherford model we studied, since the energy loss is continuously, so that's why the spectrum must be continuous. But already we have studied that the spectrum of hydrogen is line spectrum is there. So this line spectrum is explained by this Bohr's atomic model. In the Bohr's atomic model, it is given that when an electron jumps from higher energy to the lower energy, when electron jumps from higher energy to the lower energy, it emits energy in the form of the quantum. In the form of the quantum means that will radiate energy, definite amount of energy. And if the definite amount of energy is radiated, it will have the definite frequency and definite wavelength. So for one transition, you are getting one frequency. For the second transition, you are getting 7 frequencies, second wavelength. For the third transition, you are getting the third frequency and third wavelength. So that's why the different lines you are getting. So what you studied, the energy expression, what is given in Bohr's atomic model, that energy expression we will take here, and from that energy expression we will derive the expression which was given by the Balmer, and both are almost same. So by this way we can say that Niels Bohr model is successful. So first point, we are going to study that explanation of the stability of atom. How this Bohr's model explain the stability of atom from the second postulate of the Bohr's atomic model. What is the second postulate? The energy of an electron, in the orbit does not change with time. The energy of an electron in the orbit does not change with time. It means an electron moves in same orbit and energy of electron does not change. So this model explains the stability of an atom. It is given when electron revolve in a particular orbit, the energy of the electron will not change, and if the energy of the electron will not change, so that electron can move permanently in that particular orbit, in that particular energy cell. So this electron will not fall into the nucleus, and by this way the stability of atom is explained. Because in the fourth module we studied that James Clerk Maxwell gave that when a charged particle rotates under acceleration. But here, since it is given in the second postulate, when the electron revolves in a particular orbit, its energy will not change. If the energy of the electron will not change, so it can remain permanently in a particular orbit, and stability of atom is explained. So now the second explanation of atomic spectrum of hydrogen. Second explanation, that explanation of atomic spectrum of hydrogen. So the second one is explanation of the atomic spectrum. Explanation of the atomic spectrum of hydrogen atom. So how this Niels Bohr model explained the hydrogen spectrum. So Bohr's model explained the presence of large number of lines in hydrogen spectrum. Bohr's model explained the large number of lines in hydrogen spectrum. Bohr's model explained the large number of lines in hydrogen spectrum. According to Bohr's theory, according to Bohr's theory, when an electron de-excites, from a higher energy level, to a lower energy level, it emits energy. According to the Bohr's theory, when an electron de-excites means when you heat any substance, electron will go to the higher energy state. That electron is called excited electron. And when that electron is coming to the lower energy state, that will emit energy. That is written, according to the Bohr's theory, when an electron de-excites from the higher energy level to a lower energy level, it emits energy. Thus the emitted energy is quantized. Thus the emitted energy is quantized. Thus the emitted energy is quantized and corresponds to a definite frequency. And wavelength. Correspond to the definite frequency and wavelength. This forms the basis of the basis of existence of a large number of well-defined lines. Well-defined lines in the atomic spectrum of hydrogen. In the atomic spectrum of hydrogen. Just to see what you have written. Bohr's model explained the large number of lines in hydrogen spectrum. This Bohr's model explained the large number of lines in hydrogen spectrum. According to the Bohr's theory, when an electron de-excites means when it is coming from the higher energy state to the lower energy state. So according to the Bohr's theory, when an electron de-excites from higher energy level to a lower energy level, it emits energy. Thus the emitted energy is quantized. Quantized means that is the fixed amount of energy. Thus the emitted energy is quantized and corresponds to definite frequency and wavelength. This forms the basis of existence of large number of well-defined lines in atomic spectrum of hydrogen. So in the atomic spectrum we have seen that different lines, because for one transition, one frequency and wavelength, and like that many transitions will be there. So because of the many transitions you are getting the different lines. So now we will take the energy expression, and from the energy expressions we derive the derivation for the wave number that was given by Balmer, and both are matched. So by this way we can say that this Bohr's theory explained the hydrogen spectrum. So just you see, two energy levels are given, that energy levels N2, and this is the energy level N2, and this electron is present here. Electron is present here, and electron is de-excited, means it is coming to the lower energy state. So you studied that energy of electron in nth orbit, that you studied En is equal to 1 upon 4 pi epsilon naught whole square 2 pi square me power 4 upon n square h square. That expression you have studied, that energy of electron in nth orbit. And now just you see, two orbits are given, n1 and n2. So for n1 energy level, so En1 is equal to minus 1 upon 4 pi epsilon naught square into 2 pi square me power 4 n square h square. This is the second. And for N2 energy level, so En2 minus 1 by 4 pi epsilon naught whole square 2 pi square me power 4, this is N1, and this is N2 square h square. Now the change in energy delta E. So delta E is equal to En2 minus En1. So that values what you have written here, that you can put here. So minus 1 upon 4 pi epsilon naught whole square 2 pi square me power 4 upon N2 square H square minus. When you put here that En is minus, so that will become positive. So 1 upon 4 pi epsilon naught whole square 2 pi square Me power 4 upon N1 square H square. So now we can take the common. So just you see, after this you can take delta E is equal to 1 upon 4 pi epsilon naught whole square into, only N1 and N2 are different, so rest you can take common. So 2 pi square Me power 4 upon H square. So that will come here 1 upon N1 square minus 1 upon N2 square. That you can imagine that equation number 3. Now you know that delta E is equal to H nu. Already you have studied. And then you have studied that C is equal to mu lambda. Then mu is equal to C by lambda. Then delta E is equal to SC by lambda. Then again you have studied that mu bar is equal to 1 upon lambda. This is the wave number. Wave number is the reciprocal of the wavelength. So that you can write delta E is equal to SC and mu bar. This is equation 4. So just you see delta is equal to that energy expression, and then both are equal. So from third and fourth, we can take, so what do we take? That SC mu bar delta E is equal to 1 upon 4 pi epsilon naught whole square 2 pi square Me power 4 H square 1 upon N1 square minus 1 upon N2 square. So we can write here mu bar 1 upon 4 pi epsilon whole square 2 pi square Me power 4. If you take here, then you will get H cube C 1 upon N1 square 1 upon N2 square. Then mu bar is equal to R 1 upon N1 square N2 square, where R is the Rydberg constant. So where R is equal to 1 upon 4 pi epsilon naught whole square 2 pi square Me power 4 H cube C, and R is called Rydberg constant. R is called Rydberg constant. By substituting the all values, by putting all values means pi m e h c m1 upon 4 pi epsilon naught. By putting all values, the value of R is found. R is equal to, what value is found? 1.09679 into 10 raised to power 7. That is meter inverse. R is equal to that 109679 centimeter inverse. So if you remember that when you have studied hydrogen spectrum, this value was there 10, 96, 77, 10, 96, 77, that value was there, and here you are getting 10, 96, 79. So this is almost same as it was given by the Bohr. So that's why this theory explained the hydrogen spectrum. The value of Rydberg constant, the value of Rydberg constant, the value of Rydberg constant is almost same, as it was given in Bohr formula, as it is given in Bohr formula. So Bohr's model explained. So Bohr's model explained hydrogen spectrum. So the value of the Rydberg constant, it is coming 10, 96, 79, and when it was given in Bohr formula, it was 10, 96, 77. So almost same. The value of the Rydberg constant is almost same as it was given in Bohr formula. So the Bohr's model explained the hydrogen spectrum. Then this is the explanation. Then diagram, once I have given you, but once again you can see how the different lines are obtained in hydrogen spectrum. So just you go through the energy level diagram. So energy level diagram, if you take, that is equal to N is 1, then N is 2, you can write N1, you can write N1, N2, N3, N4, N5, N6, N7, like that. You can take that up to infinity, that will go N8. So when atom is heated, electron will go to the higher energy state. When they are coming to the lower energy state, they will radiate energy, definite amount of energy, definite frequency will be there. So if the electrons are coming from the second to the first, or to the first means from the higher energy state, they are coming to the lower energy state. So you are getting Lyman series, that is coming in ultraviolet region. That will go up to the here infinity. Then if they are coming to the second energy state, if they are coming to the second energy state, so that will be the Lyman series. This is coming in visible. Then Balmer series. Balmer series. Balmer partial bracket form. So next one is this one. Balmer partial. Then Balmer partial bracket. So these three are in hydrogen. You must be thinking, in hydrogen only one electron is there. Then how it is possible that these many number of lines are coming? So I want to tell you, when you take hydrogen in a discharge tube, you are not going to take a single atom. Many atoms are there. You know that in one mole, how many atoms are there? 6.02 to 10 raised to power 23 atoms are there. So if you take some amount of hydrogen, 1 gram, 2 gram, then many atoms are there. And when you apply the electric discharge, then electrons are going to the higher energy state. And these electrons are called excited electrons. And they cannot remain permanently. So what will happen? They will come to the lower energy state. So from that excited, if they are coming to the first Lyman, second if they are coming, you will get the Balmer series. If they are coming to third energy state, Paschen, fourth bracket and fifth full. Like that you are getting the 5 series. Some more series are also there, but in the syllabus only 5 series are given. So in this video up to